I'm Dr. Abdul Hamid. Today we will discuss about the elastic behavior of materials. That is elective B paper, paper 5. Today we'll discuss about elastic behavior of materials. Right. Today we will discuss about the elastic behavior of materials. Elastic behavior of materials. Okay. So in this elastic behavior of materials, so first uh, we'll discuss about what is uh, elastic deformation. Then we will move to the plastic deformation. Then after we will see the plastic deformation of single crystals. We'll see. Then we'll see the deformation of slip. Means what is slip? We'll see. Then we'll discuss about the slip and twin dislocation theory. We'll discuss, and we'll see the what is twin deformation theory and slip dislocation theory. We'll see here, and we'll see some properties and comparison of both the twin and slip deformation theories. So we'll compare. Okay. So first of all, what is deformation? We should know. Okay. So then if we know the deformation, what is deformation, then we'll go into the details of different types of deformations you have and what types of deformations are there, we'll see here. So if you take the deformation in case of the materials, if you take this deformation of the materials can be happen, otherwise it can be takes place by applying some external force or by some different physical or chemical processes. That means if you apply some physical process or chemical process onto the material, or by applying some external force onto this material, the deformation of the materials is going to be takes place. Yeah. So generally, if you see in case of materials, these materials will undergo the deformation by applying some load onto it or applying some external force onto it. So if you apply some load, then what will happen uh, basically by applying some load onto the material, the deformation, whichever it is going to be takes place. That deformation, it has been divided into two types. One, we will be calling it as a elastic deformation. We are going to be called. One, we will be calling it as a elastic deformation. And second type of the deformation which we have is we calling it as a plastic deformation. We are going to be calling it as a plastic deformation. These are the main two types which we have been classified the deformation. And coming to this elastic deformation, if you take in the case of this elastic deformation, so generally when you apply some external force onto material, some things are going to be changed in the material. So once it is changing, it's maybe lengthwise or area-wise, some it is going to be changes when we apply some external force. Then after some time, if you remove the external force which we have applied on the material, what will happen means this material will regain its original position as well as the shape it is going to be regains. Then the type of deformation we'll be calling it as what elastic deformation we are going to be called. Okay, understand? Elastic deformation is nothing but once it is a temporary deformation, once after removal of this external force, it is going to be regain its original shape and position. It is going to be regained. Then if you go for this plastic deformation, this is another type of deformation we have. In the case of the plastic deformation, what will happen means it is a non-recoverable deformation we can call. Otherwise, we'll be calling it as a permanent deformation. We are going to call this plastic deformation. Now, this after the removal of some external force, whichever we have been applied, this what we call material, it does not regain its shape or position, whatever it may be, which it is prior to the force which we have applied. So this we will be calling it as a plastic deformation. You are going to be called. So this elastic deformation is just simply it is a temporary deformation which is having. Whereas if you go for this plastic deformation, it is not a temporary deformation, but it is permanent deformation you are going to be called. This elastic deformation is a temporary deformation, whereas plastic deformation is a permanent deformation you are going to be have. Okay. If you note these two deformations, like plastic and elastic deformations, if you look into two types. If you look into these two types, these two are not they are not time dependent or time independent. Means they are not at all dependent on time as well as they are not at all independent of time. So this is what about the two types of deformations we have. And then one more thing is if you take any metals, if you take so these metals exhibit less elastic and more plastic deformation. So if you means that metals, whichever we will take, mostly they are going to be have the plastic deformation even at room temperature also. Generally, they have very less metals. Otherwise, all metals they are going to be exhibit less elastic deformation. They are going to be exhibit. Okay. And however, if you do go for higher temperatures, at lower temperature, this is going to be happen. Whereas if you go for higher temperatures, so at the higher temperatures, what will happen means they are more tuned to this plastic deformation. Okay, at higher temperature, more they are tuned to plastic deformation. Okay, so that is elastic deformation is what temporary deformation we call, and plastic deformation is a permanent deformation you are going to be called here. And if you take this elastic deformation in detail, if you go, when the materials, if you consider, and these materials, if they are subjected to some force or load, in the case of this elastic deformation, if you are applied some force or what we call a load is applied onto a material, then they behave actually elastically, they behave. Okay, they behave like elastically. Like if you apply some force on a rubber, like that means it is after removal, it regains its original position. So after removal of this, they are going to be get back to its original size as well as the position. Okay, and moreover, these elastic properties of the materials are found to be independent of imperfections. That means if any material, if it is having some imperfection at inside, that means some dislocation will be there or some gap will be there inside, some vacancy will be there inside. So they don't depend upon these vacancies or dislocations. So they are independent of these dislocations, this elastic deformation. Okay. So if you see the deformation here, so generally what will happen means if you take any what we call any material if you take. So suppose say that this is the one atom which is there inside of what we call any material. So this bonding like this, they are bonded. So all these atoms are sharing and they are forming some bond here. So this is the shape of a material. Actually, when we have not applied any load on or when we have not applied anything onto that what we call a force or load when we have not applied. This is the position of the atoms which are there in a material. So thereafter, suppose some load is applied on this one. So some load is applied, otherwise some tension is applied. So then automatically what will happen means this atom's shape it is going to be changes. So that means the position of these atoms which are present. So these are going to be changes here in this manner. Okay, so like this means uh, here the shape and in this direction or in this direction, if you are applying some load, automatically you see this is the shape which we have here, and here it has been what we call elongated. So it is elongated as we have applied some load onto this one. So some load when we have applied, the otherwise some tension is applied onto this one if the material, the atoms which are elongated. Otherwise, when we compress this material, what will happen is the shape of this, it is going to be changes in this direction when we compress. Okay. So when we compress in this manner, so in this manner, they are going to be changed. That means you see in this direction. So this is how it is going to be happen inside of a material. So this is material with which it is having without applying any load onto this metal. This is actually the original shape of this atoms which are present without any load. After applying some load, it is some tension is applied. So elongation is occurring here, and here when we compress that metal or material, so this is the shape which is going to be takes place. So this is how the elastic deformation is going to be takes place in a material. Okay, and generally, if you see this. Plastic elastic deformation. So elastic deformation is an ideal deformation in which the appearance of materials does not change after removal of the force. That means once if you remove this tension or this compression, if you remove, it is going to be regains its original shape. So it obeys the Hooke's law actually. It obeys the Hooke's law here. So Hooke's law it is going to be obeyed. So that Hooke's law is nothing but within the what we call within the limits. If you are applying, then then there will be no change if you remove this what we call stress or force from that one. If you remove, it is going to be regains its original position. That means it should be the force whichever you are applying should be within the range which you are going to be have. So generally, if you see the stress and strain curve which obeys the Hooke's law, so this is the strain which it is having, and this is the stress if you are having. So here generally it will be in this direction you are going to be have. So stress. So up to this point, we'll have some limit. So this up to this region, whatever may be the region which we have this, we will be calling it as a elastic region. Okay? Elastic region. So if the stress is beyond this, if you are applying in this, if you are applying, then what will happen means the plastic deformation is going to be occur. Okay, plastic deformation. So in the case of the plastic deformation, if you see the plastic deformation, when we uh, mm, apply the stress, this stress, whenever we are applying, the stress is no longer proportional to the strain, and therefore plastic deformation is going to be occur. That means if it is beyond the limit of this point, if you are having, then stress is no longer proportional to the strain, and therefore the plastic deformation is going to be occurs. So in the case of the plastic deformation, as we studied, it does not comes back to its original position. It does not comes back to its original position here. Okay. So this is what plastic deformation you are going to be have. So generally, this plastic deformation can occur under what we call under torsional or a compressive or a tensile stresses only. Okay. So if you apply some what we call kind of torsional or compressive and tensile stresses, if you are applying, the plastic deformation is going to be occurs here. And the rate of plastic deformation deploys, that means it depends on the applied stress from a strain rate and also it depends upon the temperature also. Okay. So the ability of materials to undergo plastic deformation is called it as a ductility we are going to be called here. Okay. The ability of materials undergo plastic deformation is called ductility we are going to be called. Okay. So this is what about the plastic deformation which we have. Okay, plastic deformation which we have here. And next, we'll see uh, plastic deformation in the case of the single crystal. So here we'll see next topic is plastic deformation. Plastic deformation of single crystal. Plastic deformation of the single crystal. So this plastic deformation of single crystal is mainly affected by shear movement of a part of a crystal to another part of a crystal. Okay, so there will be a change in its movement of a part of crystal to another part of crystal. So under the action of the what we call under the action of the some tangential stress, that means if you are applying the tangential stress, then will be crystal is affected by shearing movement of part of crystal to another part of the crystal. Okay, so that is what we call it as a plastic deformation of a single crystal. We are going to be called. So the main reason why this plastic deformation of a single crystal is going to be occurring is you'll be having two things. It may be happen. One we'll be calling it as the log slip. We are going to be called. We'll be calling it as a log slip, and another one we'll be calling it as a by twinning. By twinning. By twinning. So this plastic deformation of a single crystal is occurring by the two processes. One is log slip, and another one is by what we call a twinning. We are going to be called. So these are the two main processes which occurring. So if you take in the case of the slip here, that is in the case of the slip. So this slip is nothing but one part of the crystal is displaced parallel to the remaining part. That means how this is going to be happens means in the case of the slip. So generally, this if we are having, so it's going to be slips like this. Understand? So like this. So the slip, how it is going to be happens means in the case of the slip, one part of the crystal is displaced parallel to the remaining part. So this one and this one, they are going to be slip parallelly. So along the line, which is called as a slip, we are going to be called. Whereas in the case of the twinning, what will happen means the rearrangement of the crystal is going to be takes place into a new position. Okay, rearrangement of the crystal is going to be takes place a new position. So simply here it is slipping on the same what we call a crystal to other place. Whereas in the case of this twinning, what will happen means one part of the crystal is displaced. Uh, okay, one part of the crystal is displaced. Otherwise, we can say that in twinning, rearrangement of the crystal is in its new position. The entire position it will be changes. That means here, actually, if you are having a initially this is the crystal if you are having. Okay, so uh, this is what the crystal initially it is having like this. So what will happen means entirely it will changes. Maybe it will goes in this manner. Okay, maybe right. So it will goes in this manner. So here the entire position. Here you see parallelly, this is the case of slip, it is going to be happen. And this is what, if you see, this is in the case of this water twinning, it is going to be happen. That means its position in the entirely, it is going to be rearranged in the case of the twinning. So that is what the difference which we have. So in the case of the slip, it is going to be changes its part parallelly, it is going to be changes, whereas in the case of the this twinning, entire rearrangement of the crystal into new position, it is going to be takes place. And this new position, if you take this new position, is mirror mirror symmetrical to the original position. Mirror symmetrical to the original position. That means entirely it will replace us to other part. If you see that one, it will be mirror symmetrical to the original position it is going to be have. Okay. So the plane of the mirror symmetry is called twinning plane. We are going to the plane of the mirror symmetry is called twinning plane. We are going to be called. So here the atomic planes are arranged in parallel to the twinning plane through different distances. They are going to be arranged. Okay. And if you see the orientation, the reorientation of crystal lattices has been taken place due to the twinning. The orientation of this crystal will be reoriented. That is, crystal lattice has taken a place due to twinning. It is going to be happen. Okay, right. So this what we call if you take crystals like BCC and FCC, uh, in the case of this BCC crystal, and as well as the in the case of the FCC, this what we call this twinning effect is going to be observed at low temperature. Okay, BCC and FCC metals, whichever we have, these BCC and FCC metals, they are going to be observed twinning at low temperature. They are going to be observed, and even in the case of the HCP metals also, in the case of the HCP metals also, we can observe this both twinning as well as the slip. So this both we can observe this twinning as well as the what we call slip. It is going to be occur in the case of the HCP metals. Only for BCC and FCC metals, they are going to be occur this what we call twinning, and that too at low temperature they are going to be observed here. So this is what due to the slip, the log slip as well as the twinning, the plastic deformation in a single crystal is going to be happen here. Okay. So next we'll see the deformation of slip. We'll see the deformation. Deformation of slip. So slip systems of FCC, BCC, and as well as the uh, HCP lattices will have. So this can take place along the planes for dense packing of atoms and depends upon the crystal structure. So if you take FCC crystals, okay, FCC crystals, that means FCC metals, whichever we have. So generally these FCC metals are like aluminum or nickel or copper. You'll have all this comes under this FCC metals. So in these FCC metals, the slip is going to be occur in the plane of one plane. In this one plane, they are going to be occur, and in the direction 110. The direction 110, you are going to be occur. So four slip planes in three directions you are going to be there. So there, this will be leads to total 12 equivalent slips. Okay, four planes and three directions it is going to be occur. So total 12 equivalent slips will be there. And the second one, if you take the case of BCC, the case of the BCC. So this BCC will be developing slip in three different planes. It is going to be developed. That is 110 and as well as the 112 and as well as the what we call 123. In these three planes, it is going to be developed this slip in the BCC metal in these three planes can be developed, and it have only one direction, that is a one direction it is going to be have. Total leads to here around 48 slip systems it is going to be have. It is going to be have 48 slip systems in this case of what we call a BCC structure. And if we take the another one which we have is HCP, another one HCP. So for this one, the value of C by A should be greater than or equals to 1.63. The value of C by A should be greater than or equals to 1.63. Here the slip develops in the base planes only. Slip develops in the base planes only, and moreover, under this BCC, like in the case of the magnesium or zinc, these materials have a what we call a lower ductility are going to be have when we compare with the FCC and the BCC metals. It is having very lower ductility. Okay, so this is about the deformation slip you have. And next we'll see another one, which is the slip and twin dislocation theory. Slip and twin dislocation theory. First, we'll see the twin deformation theory. Next one is a twin deformation deformation theory. So in this twin deformation theory, twinning already we have seen. What is twinning is nothing but it is a movement in the lattice. It is going to be have the movement. It's going to be have the movement in the lattice. Okay, it is going to be have movement in the lattice. As the movement in the lattice, which results in two symmetrical parts, but differently oriented planes. So it is going to be have the two symmetrical parts you are going to be have, but different planes because the movement of the lattice is going to be takes place. So there will be what we call two symmetrical parts with the different orientations you are going to be have, and the amount of movement of plane whichever it is going to be happen, the amount of movement of such plane is proportional to the distance between the twinning planes, and therefore mirror images are going to be formed across the twin planes here. Okay, across the twin planes here. So the twinning planes also called as a fixed planes we are going to be called, and we have like a example of the twinning planes will be in FCC crystal. If you take the FCC crystal, it is 111 plane you are going to be have twinning plane, and in the case of the BCC crystal, if you take it will be 112 plane you are going to be have, and in the case of the HCP plane, if you take, you are going to be have a 112 is the twinning plane. In the FCC crystal, it is a 111. That is 111 is the twinning plane you are going to be have. In the case of the BCC crystal metal, if you take, it is 112 twinning plane you have, and in the case of the HCP, it is 112 twinning plane you have. Okay. So generally, this mechanical twinning are produced in the case of the BCC and HCP at lower temperatures. And in the case of the FCC materials, they do not deform by mechanical twinning. And in the case of the copper, mechanical twins are produced at higher temperatures. So if you see the what is the differences between the slip and twinning, if you see here, so we'll see the differences between the slip and Slip and twinning. Let's see the differences between the slip and twinning here. So if you go for orientation, how it is taking place in the case of the slip and as well as in the case of the twinning, if you see, the orientation of the slip is generally below and above slip planes, which is the same after deformation. Okay, the orientation of the slip, if you take here, the orientation below and above, you have the slip planes is same after deformation. After deformation is occurring, below plane and as well as the above slip planes are have the same. Whereas if you come to this, what we call twinning, in the case of the twinning, orientation causes what will happen, difference across the plane. Okay, difference across the planes. Okay, so here you will be having the same planes below and above. Here you will be having the difference across the plane you are going to be have, because in the case of the twinning, if you see, the twinning is going to be changes its position. It is going to be changes, even though if it is having the mirror orientation, even though if it is having, it is going to be changes its what we call a plane. And if you see about the movement, how the movement will be takes place in the case of the slip and as well as this twinning, if you see, in the case of the slip, it occurs at a discrete multiples of atomic spacing. Means inside you'll have the discrete multiples of atomic spacing. So there it is going to be occur this slip. Whereas if you take this twinning, the movement is much smaller in this case. Okay, movement if you take, so this movement is smaller. In this case, you are going to be have with the atomic spacing distances. Okay, and the deformation, in the case of the deformation, if you see slip deformation, slip plane is wide plane and direction is closed back direction you are going to be have. And in the case of the twinning, in twinning, every atomic plane is involved in the deformation. Twin occurs in the definite direction of the crystallographic plane it is going to be have. Okay. And for how much time it takes place and for how much times this twinning is taking place, if you see, slip plane takes place for milliseconds only. It takes for milliseconds and it takes place this what we call which one twinning, it is going to be takes place for microseconds. That means in a very shorter period of time this twinning is going to be takes place. And whereas the slip is going to be takes place for a millisecond. Means if you compare the both this slip is going to be take more time, whereas twin is going to be takes less time. And how much stress you are going to be apply in the case of the slip and in the case of the twinning, if you see, slip takes place in the slip direction and reaches to a critical value, which we call it as a critical resolved shear stress we are going to be called. And in the case of the twinning, the critical shear stress in twinning does not follow any rule. That means it does not have any rule to follow. Okay, so this is about the what we call the differences between these two. That is slip and as well as the twinning which we have. Next, we'll see the slip dislocation theory. Slip dislocation theory. So, if you take any perfect crystal, if you take, okay. So, if you take any perfect crystal, so generally the perfect crystals or ideal crystals, we can say, they don't have any what we call defects inside. Okay, they don't have any defects. So, in the case of the perfect crystals or ideal crystals, the defect will be zero. So, no defects will be there. No defects will be there in the case of the perfect crystal or ideal crystal. And the critical or shear stress can be calculated by using the formula here. That is the tau PR, which will be equals to G by 2 pi, which is equal to 0.16 G, which is equals to 0.16 G here. So this G is nothing but the shear modulus. This is nothing but the shear modulus we are going to be called. And this tau CR if you take, okay. So this is what we call it as a theoretical strength of the material. Tau CR is called theoretical theoretical strength of theoretical strength of material. Okay. So for real crystals, the crystal strength is very low. The crystal strength is very low in the case of the real crystals. The energy dislocation is E. The energy dislocation E is proportional to the length of the dislocation, that is L, and shearing modulus G, and what we call Burger's vector B have some important points here. So generally, for deformation energy, lower if we are having lower deformation energy, the P and G values, okay, B and G value, Berger vector and the G value, the shearing modulus both are low, you are going to be have, okay, for a lower deformation energy. And if you go for what we call for plastic deformation, if you go, so plastic deformation will develop for low values of B. For low values of B, this what we call plastic deformation is going to be developed, and the plastic deformation is affected by the moment of dislocation. Okay, that will be affected by the moment of dislocation. Okay, so next dislocation will move along the plane of dislocation line and Berger vector B. Okay, that is what you are going to be have some important relations between these, and as well as what we call by applying some stress, the half plane of the top crystal combines with lower portion of the nearby plane and forms a single atomic plane here. Okay, so this type of process goes on, and finally dislocation moves to the top portion of the crystal. This is what the slip dislocation theory is there. And here, uh, this tau r, that is a shear stress, can be related. This tau r can be related by the relation sigma cos phi 1 cos phi 2 here. So here sigma is nothing but the tensile stress, and here tau r already we have seen, that is shear stress, shear stress. So they are related with tau r is equals to sigma cos phi 1 phi 2. Here if you take the phi 1 and phi 2, these are the angles. So especially if you go for this phi 1, this phi 1 is the angle between the normal of slip plane and tensile axis. Okay, this phi 1, what actually it represents means, it is the angle between the normal slip, the slip, normal slip plane, normal slip plane, okay, between the normal slip plane and what we call tensile tensile axis. Okay. And if we come to this phi 2 is the angle between the what we call a tensile axis and slip direction. And slip direction we have. Okay. So this is the relation how we can get here. Suppose uh, suppose if what we call if phi 1 and phi 2 values if you take, so if they are equal, that is nothing but suppose if you take this phi 1 plus phi 2 is equal to 90 degrees if we are having. And that too, if this phi 1 angle is equal to 45 degrees if it is having, and similarly if it is having phi 2 is equal to 45 degrees, we know that the value of cos 45 is equals to 1 by root 2 it is having. So here if you substitute to get this tau CR, okay, tau CR, which is equals to sigma times cos 45. Again, we have cos 45. So therefore, it will be sigma into 1 by root 2 into 1 by root 2. So it will become so much sigma by 2 it becomes. Okay, it will become sigma by 2. That means uh, from this above equation, whichever we have written here, it is clear that the result stress will be always less than the half of the tensile stress you are going to be have. Okay. So and talking about this, what we call the values T tau CR values. So for different cases, if you see this for pure materials, okay, for pure materials, if you take, so for pure materials, this tau sigma is very less you have, and um, thin films, if you take, these thin film surfaces have more critical stresses you are going to be have, and this tau CR value is going to be tau CR value is going to be increases with thermal mobility and as well as the um, with the thermal mobility, tau CR value increases. And also, if you increase more amount of temperature, its value is going to be decreases. Okay. And this tau CR increases with the what we call a deformation factor also. So the value is going to be decreased with the deformation factor. Okay. So this is what we have. So we have seen about actually what is the deformation we have seen. So deformation is nothing but when you take any material, if you take, if this material is subjected to some external force, if you are subjected, then the change in the material is going to be occur. The change in its forms maybe in dimension, in whichever may be the dimension, we will be calling it as a deformation. That means if a material is undergoing some changes by applying some force, then we will be calling it as a deformation is going to be happen. And this deformation is having two types. One is a recoverable, another is non-recoverable. Uh, whereas recoverable deformation is called it as what elastic deformation we are going to be called, and whereas non-recoverable deformation is called it as a plastic deformation we will be calling. So both these recoverable deformation and non-recoverable deformations are time independent. They are not dependent of time. And we have seen about this vertical plastic deformation of a single crystal we have seen. So the plastic deformation of a single crystal occurs by the two mechanisms. One is due to the deformation of the slip and due to the twinning we have seen. Okay. So what is what we call a slip we have seen. What is the twinning also we have seen. Slip is nothing but it changes its plane only. It does not change its position. Whereas twinning, if you take, it is going to be changes its position, but it will be like a mirror means mirror replacement of the original you are going to be have. It changes its entire position, but it will be as it is previously, which we have. So this is about some deformations and different types of deformations we have seen. And in the case of the single crystal, how the deformation is going to be happen, that is also we have seen. The comparison also we have seen. That is how the both deformations, like a plastic deformation and as well as the elastic deformation we have. Next, the comparison of this slip as well as the twinning also we have seen. That means the changes which are there for this twinning and slip. Mostly in the case of the orientation, slip, the above and below slip planes will be same. In the case of the twin, the entire what we call differences occurs in the plane. In the case of the momentum, slip momentum will be like discrete multiples of atomic spacing will be there. And in the case of the twinning, momentum is much smaller than the atomic spacing distance you have. And in the case of the deformation of the slip planes is wide plane and direction is close path direction. And in twinning, every atomic plane is involved in the deformation. Time, if you see the time which occurs slip will be um, in the order of milliseconds you have, and in the case of the training, it is going to be having the order of microseconds you have. The stress, if you see, slip takes place in the slip direction and reaches to a critical value, called it as a critical resolved shear stress we are calling. And in the case of the twinning, the resolved critical shear stress in twinning does not follow any rule, it does not follow. So this is about the elastic behavior of the material in the case of the mechanical properties. So different types of deformations and the different types of deformation also we have seen here. हाँ बोल, अभी हो गया क्लास, अब निकल रहे हो? आप लंच बाहर कर रहे क्या?